We all feel time, right? It's the rhythm of our lives, the ticking clock on the wall. It just always moves forward. It feels like the most real thing there is. But what if I told you that for the physicists trying to figure out a theory of everything, time is their single biggest nightmare? That when they write down their deepest, most fundamental equations, the clock just isn't there.
It is a totally shocking question, I know. It sounds like something straight out of a sci-fi movie. But this isn't just some late-night philosophical debate. This is a real, deep, mathematical paradox that pops up when we try to smash our two best theories of the universe together, Einstein's general relativity and quantum mechanics.
All right, so let's dive right into this. Physicists call it the problem of time, and it is one of the biggest roadblocks in modern science. What it suggests is that our best theories, when you push them to their limit, might be describing a universe that is completely, totally static, frozen.
The implication here is just staggering. When you try to combine the math of quantum mechanics with the math of gravity, the little t for time, the variable that makes everything happen, that drives all change, it just vanishes. It cancels out of the main equation. And you're left with this description of a universe that doesn't evolve at all. It's what they call frozen formalism, like having a beautiful photograph of the universe, but no movie projector to ever make it play.
Now, this is a huge problem, and you don't have to be a physicist to know that any theory describing a universe without change or evolution is just, well, it's wrong. It's a non-starter. This paradox has had scientists scratching their heads for decades. So let's take a quick look at how the biggest theories out there have tried, and pretty much failed, to solve it.
This table really lays out the whole dilemma. The most straightforward approach, canonical gravity, runs you straight into that frozen universe we were talking about. So that's a dead end. Then you have loop quantum gravity, which is pretty clever. It says, hey, maybe one physical thing in the universe can act as a clock for everything else. The problem is, the theory gives you no clue which thing to pick. That leaves you with a ton of ambiguity. And then there's string theory, which kind of just throws its hands up and assumes a fixed background clock is already there, which, by the way, completely violates one of the core principles of Einstein's relativity. See the pattern here? Every major approach just hits a wall. Okay, so this kind of stalemate really suggests we need a totally new way of thinking about this. What if we've been asking the wrong question the whole time? What if time isn't some fundamental ingredient of the universe that's gone missing? What if it's something that gets built from simpler, more fundamental pieces?
This is this amazing concept called emergence. And the best way to get it is this. Think about a single molecule of H2O. It's got properties, sure, like mass and polarity, but is it wet? No, of course not. Wetness is a real physical property that emerges only when you get billions and billions of those molecules together. And here's the most important part. Emergent properties are not illusions. Wetness is real. You can feel it. And maybe, just maybe, time is exactly like that. A very real property of our universe that arises from a deeper, timeless reality.
And this brings us to a really fascinating new theory called the Conformal Emergent Reality model, or CERM for short. It takes this powerful idea of emergence and just runs with it. It proposes that not just time, but the entire fabric of space-time itself is a collective phenomenon, an emergent property built on top of a much more basic foundation.
So, how in the world does this work? Well, CERM basically says our universe gets built in 3 steps. First, you start with this really bizarre foundation, a timeless reality where things like distance and duration literally don't exist yet. The only things that are defined are angles and a very basic sense of cause and effect. Then, step 2, a catalyst, which the theory calls the omega field, starts interacting with this foundation. And then, finally, step 3, from that interaction, our familiar reality, with its measurable space and its ticking clocks, crystallizes into existence.
Okay, so if space-time just emerges, where does the clock come from? This is where CERM offers its most beautiful and elegant solution. It doesn't go searching for a missing clock. It builds a brand new one directly out of the very fabric of the universe itself. This new clock is called prototime, and it's represented by the Greek letter tau. Now, this isn't some abstract idea. It's a real, physical, measurable thing that you can get directly from the curvature of geometry. You can think of it like a clock that's built into the very shape of the universe, and it actually ticks faster where gravity is strong and space is all curved, and it ticks slower where things are flat. The universe is the clock. And the existence of this physical geometric clock leads to something truly amazing, a brand new kind of quantum uncertainty principle. But this one doesn't apply to little particles. It applies to the very nature of geometry.
This works just like a really famous idea in quantum physics. You've probably heard of Heisenberg's uncertainty principle, right? You can't know a particle's exact position and its exact momentum at the same time. The more you know about one, the less you know about the other. Well, CERM proposes a geometric version of that exact same idea. The more precisely you measure the curvature of some region of space, the less precisely you can know its proto-time and vice versa.
And here it is. This is the punchline. This new uncertainty relation is the engine that drives change. It creates this fundamental quantum fuzziness that literally forces the geometry of the universe to evolve and change. And just like that, the static, frozen picture is gone. It's replaced by a dynamic, living, breathing cosmos. All thanks to this deep quantum geometric link. The problem of time is solved.
So that's incredible. The problem of time gets solved. But the implications of a model like this go so much deeper. It forces us to rethink some of our most basic ideas about what reality even is. This quote from the paper just captures the whole shift in perspective perfectly. Our entire world of space and time is a secondary effect. It's a derivative property of a much more fundamental, timeless, geometric reality. It's like we're living on the surface of something much deeper and much stranger. Let's just break down what this really means, because it gets wild. In this new picture, causality, that strict rule that a cause has to come before its effect, that's not fundamental either. It's an emergent property. At the deepest level, the order of events is all fuzzy. And quantum entanglement, that spooky action at a distance that baffled Einstein, it's not spooky anymore. It's just a direct, timeless geometric connection between two particles. And the arrow of time, the reason it always flows forward, that also emerges from the collapse of a quantum superposition of all the different possible causal paths.
And this brings us to one final, really profound thought. CERM solves the problem of time not by finding some missing clock, but by revealing that the universe is the clock. It shows that time isn't an illusion. It's a real, physical feature that emerges from a timeless foundation. So, if something as fundamental as time is actually built on a deeper geometric truth, what other big features of our reality are not fundamental at all, but are just waiting for us to discover the deeper layer from which they emerge?